Okay, we're going to get into chapter 3 now and talk about the composition of substances and solutions. Okay, so solution chemistry. So here's an image of a swimming pool, and you look at it, and it's nice, clear, beautiful water, right? But if you were to look at it on the molecular level, you would see a lot more than just water, right? So all the stuff that's in there, we can't see. There's a ton of ions in this swimming pool, all the chlorine and everything that they put in it that we don't see. And so the water in a swimming pool is a complex mixture of those substances. And their relative amounts must be maintained at the proper concentrations. Okay? So concentration is kind of the key that we're looking at there when we're talking about solutions and trying to understand how many of something are in an area of that swimming pool. And that's basically considered the concentration of it. Okay? So, and concentration doesn't change with amount. So I can either have the whole swimming pool, or I could take a cup and scoop out some of the swimming pool into the cup, and the concentrations of the ions would be the same in the swimming pool as they would be in the cup. The concentration doesn't change. Okay? Just by the amount. It's an intensive property, concentration. So just like density is a concentration unit. There are other concentration units that we're going to look at to understand the properties of these solutions. Okay? Okay, so concentrations are based on amounts of substances within a solvent. So a solute is what the term is for the thing that's being dissolved or in the lesser amount. And the solvent is the thing that is in the greater amount, the greatest amount. Okay? And concentrations are defined either by mass per mass ratios, mass per volume ratios, mole per volume ratios, or mole to mass ratios. Okay? And these are intensive properties. They don't change with the amount. And to understand the amounts of solute or solvent in a solution, we must know how to calculate the mass of these chemical compounds, okay, or chemical compound of the substance. So, if we're willing to identify the concentration of something, a substance inside of this swimming pool, then we have to be able to calculate the mass of them. If we're going to do mass per mass ratios or mass per volume. Or we need to figure out how to find the moles. And that might be a new term. Maybe not to everybody, but it might be a new term to some of you. The mole is a measurement of basically mass, but more so on the atomic level. Okay? And once we understand that mole concept and how it relates to mass, we'll be able to really work out these ratios. Okay? So, how do we determine the formula mass of an item? So here we have carbon tetrachloride. Okay? And if we wanted to find the mass of carbon tetrachloride, then this would be the best way to do it. You make a list. Okay? You have your carbon, you have hydrogen, and you have chlorine. How many carbons do I have in this formula? CHCO3. Well, I have one carbon, one hydrogen, and 3 chlorines. Okay? All right. Well, what is the mass of each of those individually? Well, the mass of a single carbon is 12.011. The mass of a hydrogen is 1.008, and the mass of chlorine is 35.45. So now I just need to find out what the mass of everything is together. So chlorine has a mass of 12, hydrogen a mass of 1, and 3 chlorines have a mass of 106.35. And then add it together, and I get a final mass of 119.37. Now, the units of that would be in grams per mole, and we'll talk about what that means per mole in just a little while. Okay? But that would be the units of my mass. so many grams. So basically, if I measure out 119.37 grams of chloroform, okay? I said carbon tetrachloride earlier. I was forgetting this hydrogen. Okay, but of chloroform there, then it would if I measured out 119.37 grams of it, that would mean that I have 1 mole of it, because it's 119 grams for every mole. So once we figure out that mole concept, we'll have a better idea what that means. Okay. You can also look at it in units of atomic mass units. On the atomic level, it would weigh 119.37 atomic mass units, which would include all the protons and the neutrons. There would be together 119, approximately 119 protons or neutrons, or 120 protons and neutrons on a different molecule, or 118 on another one. Okay, but the average would be 119.37. Okay, because that's an average atomic mass. Okay, so here's another example. Now, one way might be easier for you that I really like doing is just writing it C9H8O4. So this already tells me how many I need to multiply everything by. Okay, C9 carbon weighs 12.011, so I multiply it by 9 and I get 108.09. Hydrogen times 8 is 8.064 to be exact. And oxygen times 4 would be 64.00. And then you just add those up, 180.15 grams per mole, or atomic mass units, okay, for that item. So the formula tells me how to find the mass of these. Okay, so we really need to be able to identify the mass of these items. Very easy. What am I trying to say? Without difficulty. I mean, should be just like something that you can do by second nature. Okay, finding these masses, and it's pretty intuitive how to do it. So I don't anticipate you'll have much trouble. Here's another formula: C13H18O2, same way. Okay, 13 carbons, 18 hydrogens, 2 oxygens. Find the masses, add them together. Okay. Now, when we look at an ionic compound, ionic compounds are crystalline structures. Okay, but you're going to find the mass in the same way, because they're in their ratios, their lowest ratios. So if I find the mass of a single sodium and a chlorine and add them together to 58.44, then once again, if I have 58.44 grams of sodium chloride, then I know exactly how many atoms of sodium and chlorine I have in that crystal, in the substance I weighed out on my scale. Okay. All right. So now here's one that might be a little trickier, because you see the parentheses, right? So has 2 aluminums and 3 sulfates. So when I make my list, I want to say AlSO. Okay, I have 2 Als, but how many sulfurs do I have? How many sulfurs? 3. Okay, I have 3 because that gets multiplied in. How many oxygens do I have? Say it again. 12. Okay, so I have 12. So that's how I'd make my list there. And this is what I would get. Okay, so those numbers have to get multiplied into the parentheses whenever you have them, to identify the number of elements in the compound. Okay. Okay, so now we're going to talk about the mole. So I've been telling you these numbers here represent grams for every mole. Well, what is the mole? Well, the mole is a quantity. It's an amount. So just like 1 pair equals 2, or 1 dozen equals 12, 1 mole equals an actual number, 6.022 times 10 to the 23rd, or there it is, written out. It's a very large number. Well, we have to have a very large number like that because atoms are very, very tiny. We don't see them because they're so small. This room is filled with oxygen and nitrogen, gas, carbon dioxide. But we don't see those molecules because they're so tiny. We can't see them. Okay? But they're here. They're keeping us alive. So we know they're here. Okay? We have to breathe that oxygen. But if one oxygen itself, it's too small to see. Okay? So we have to work with really large amounts of these things in order to have them perceivable, for us to be able to work with them in the laboratory, because you can't work with them individually as a single atom. So this is the amount that I have to work with. So if I measure out some sodium chloride in the laboratory, it needs to be to these amounts of atoms for me to be able to work with it, or else it's just too small for me to work with. I can't work with it. Okay? So this is what the mole is. It's an amount. So for every 1 mole, I know exactly how many atoms I have. Okay? So here's a short video. That'll kind of hopefully help demonstrate that.
Okay, today we're going to talk about the mole. Now I know what you're thinking. I know what a mole is. It's a small, furry creature that digs holes in the ground and destroys gardens. And some of you might be thinking that it's a growth on your aunt's face with hair sticking out of it. Well, in this case, a mole is a concept that we use in chemistry to count molecules, atoms, just about anything extremely small. Have you ever wondered how many atoms there are in the universe, or in your body, or even in a grain of sand? Scientists have wanted to answer that question, but how do you count something as small as an atom? Well, in 1811, someone had an idea that if you have equal volumes of gases at the same temperature and pressure, they would contain an equal number of particles. His name was Lorenzo Romano Amadeo Carlo Avogadro. Wonder how long it took him to sign autographs. Fortunately for Avogadro, most scientists didn't accept the idea of the atom, and there was no way to prove he was right. There was no clear difference between atoms and molecules. Most scientists looked at Avogadro's work as purely hypothetical and didn't give it much thought. But it turned out he was right. By late 1860, Avogadro was proven correct, and his work helped lay the foundation for the atomic theory. Fortunately, Avogadro died in 1856. Now the thing is that the amount of particles in even small samples is tremendous. For example, if you have a balloon of any gas at 0 degrees Celsius and at a pressure of 1 atmosphere, then you have precisely 602 sectillion gas particles. That is, you have 6 with 23 zeros after it particles of gas in a container, or in scientific notation, 6.02 times 10 to the 23rd particles. This example is a little misleading because gases take up a lot of space due to the high kinetic energy of the gas particles, and it leaves you thinking atoms are bigger than they really are. Instead, think of water molecules. If you pour 18.01 grams of water into a glass, which is 18.01 milliliters, which is like 3.5 teaspoons of water, you'll have 602 sectillion molecules of water. Since Lorenzo Romano, never mind, Avogadro was the first one to come up with this idea, scientists named the number 6.02 times 10 to the 23rd after him. It is simply known as Avogadro's number. Now, back to the mole. Not that mole. This mole. Yep, this number has a second name, the mole. Chemists use the term mole to refer to the quantities that are at the magnitude of 602 sectillion. This is known as a molar quantity. Atoms and molecules are so small that chemists have bundled them into groups called moles. Moles are hard for students to understand because they have a hard time picturing the size of a mole, or a 602 sectillion. It's just too big to wrap our brains around. Remember our 18.01 milliliters of water? Well, that's a mole of water. But how much is that? Exactly what does 602 sectillion look like? Maybe this will help. Exchange the water particles for donuts. If you had a mole of donuts, They would cover the entire Earth to a depth of 8 kilometers, which is about 5 miles. You'd really need a lot of coffee for that. If you had a mole of basketballs, you could create a new planet the size of the Earth. If you received a mole of pennies on the day you were born and spent $1 million a second until the day you died at the age of 100, you would still have more than 99.99% of your money in the bank. Okay, now we sort of have an idea how large the mole is. So how do we use it? You might be surprised to know that chemists use it the same way you use pounds to buy grapes, deli meat, or eggs. When you go to the grocery store, you don't go to the deli counter and ask for 43 slices of salami. You buy your salami by the pound. When you buy your eggs, you buy a dozen eggs. When we hear the word dozen, we probably think of the number 12. We also know that a pear is 2, a baker's dozen is 13, a gross is 144, and a ream of paper is, anybody? A ream is 500. Well, a mole is really the same thing. For a chemist, a mole conjures up the number 6.02 times 10 to the 23rd, not a fuzzy little animal. The only difference is that the other quantities are more familiar to us. So there you have it, the story of the mole, Avogadro, basketballs, and how to buy salami at the grocery store.
Okay, so when we look at the periodic table, we see that the elements have their masses, right? And these masses relate to the mole. There are, for sodium has a mass of 22.98977 grams. Grams per mole of it. Okay? So that means if I measure out on a scale 22.98977 grams of sodium, I have exactly 6.022 times 10 to the 23rd atoms of sodium, okay, in that sample of sodium. So that's how these numbers are all relating to that. These basically standardize these masses into one quantity. All of these are at the same quantity. 6.022 times 10 to the 23rd, 6.022 times 10 to the 23rd. They're all at that quantity, but just at different masses because they're all heavier. This is heavier than that. Sorry, this is heavier than that, so I need more of them, right, to establish them at that quantity. Okay, so that's the idea behind the mole. So let's look at it a little further. Okay, so carbon, mass of 12.011, has those atoms for every mole of it. Hydrogen 1, oxygen 16, sodium 22.99, chlorine 33.45. But they will all be at that same quantity of the mole, even though their masses are different. Okay, because they're heavier or lighter than the others, so that's why. So here we see each sample contains 6.022 times 10 to the 23rd atoms, or 1 mole of atoms. So this essentially is how much I would have to weigh out of these different elements in order to obtain those quantities of the mole. I would just simply have to weigh them out to these quantities. Okay, zinc to 65.4 grams, carbon to 12, copper to 63.5 grams. So you see how they did the copper? They just used wire. Yeah. So that copper wire is pure copper, and if you weigh out 63.5 grams of it, you'll know exactly how many atoms of it you have. Okay, and so forth. Okay, so here's another example. The number of molecules in a single drop of water is roughly 100 billion times greater than the number of people on Earth. So this quantity of 6.022 times 10 to the 23rd is just mind-boggling, right? It's just like such a large number. That is because atoms and molecules are so small. They're so small we cannot work with them unless we have these big amounts, large amounts of them. So there you go. There's more water molecules in that single drop, 100 billion times greater than the number of people on Earth. Okay, just in a single drop of water. That's how small these atoms are, and how we have to get a lot of them to really work with them. Okay? Okay, so now we're going to look at how do we use this concept of the mole in relation to grams and through conversion. Okay, so if I want to convert something, so here I want to derive the moles of an element from the atoms of that element. Okay, so here I'm working with potassium, and I have 5.34 times 10 to the 21 atoms of potassium. Okay, and I want to know how many moles of potassium is that, because 1 mole of it would be how much? How many atoms would I have to make it 1 mole of potassium?
6.022 to 23rd.
That's right, 6.022 times 10 to the 23rd. I don't have that many, right? So that means I have less than a mole here, but how much exactly do I have? So I would set it up in this fashion. You always start with what you're given. This is what I'm given. This is what I'm starting with. Okay? And I want to convert it to moles. So the process is atoms to moles. And so I'm going to multiply my atoms by this conversion factor of atoms to moles. Okay? So moles is on top because that's what I want to get. Atoms is on bottom because that's what I want to get rid of. The atoms units cancel, and I will be left with moles, just like it's showing me here. So this is the process. This is the process that I need to follow. Okay? So with actual numbers, when I fill it out, I start with my amount that I have. I use my conversions here. 1 mole is on top, 6.022 times 10 to the 23rd atoms is on the bottom. And the atoms units will cancel. So I'll take 5.34 times 10 to the 21 and I'll divide it by 6.022 times 10 to the 23rd. And it will leave me with 0.00887 moles of potassium. Yes, ma'am?
What's this that K stand for?
Potassium. Okay. Number 19, potassium. Okay. So if I wanted 1 mole of potassium, I would need 39.0983 grams of it. Okay. And we'll look at an example like that. But here, this is simply atoms to moles conversion. Okay, well, what about the other way? Moles to atoms. Okay, now I'm starting with the number of moles. And it could be any number of moles. If I started here with 1 mole, then this answer would be 6.022 times 10 to the 23rd. But here I'm starting with half a mole, basically, 0.567. So how many atoms is 0.567 moles? Well, I set up my conversion, take my number, multiply it by my conversion factor. But this time, I put the atoms on top because that's what I want to get to. If I'm starting with moles, I want to get to atoms. I divide by the moles here, they cancel, and I will be left with my atoms. Moles to atoms, okay? This cancels the moles, and I'm left with my atoms. That's the dimensional analysis right there, okay? It will benefit you to set up the dimensional analysis first, and then put your numbers in. Put your numbers in after you've set it all up. So, basically, I would start out, you could even write it like this. I know a lot of people like to. I even like to. Okay? My atoms on top. I want to go from my moles to my atoms. So, my moles need to go on the bottom so they can cancel. That's the dimensional analysis. Okay? It's good to do that first. And then you can put your numbers in. What am I starting with? 0.567. My conversion factor, atoms, is 6.022 times 10 to the 23rd, and the moles are always 1. And so now I can convert there, doing that. Okay? Okay? Here, we want to look at how to derive the moles of an element from the mass. So now I'm going from mass to moles. Whenever you have mass in your question, that means you are going to have to come here to the periodic table, because that's where you find the masses of these elements. So this is potassium once again. Okay? If I have 125.6 grams of potassium, how many moles of potassium do I have? Well, every 1 mole of potassium is 39.10 grams of it. So I obviously have more than 1 mole of it. Okay? So I want to know exactly how many moles I have. So I start with the grams of potassium that I have. I multiply it by the molar mass, which is 39.10 grams per mole. That's how I set it up. Moles is on top as 1. Grams is on the bottom as 39.10 grams. 125.6 divided by 39.10 gives me 3.21 moles. Okay? So there are 3.21 moles of potassium in 125.6 grams of potassium. So hopefully you're seeing that there is a very specific procedure that I can follow to do these conversions. I simply start with what I'm given. I multiply it by my conversion factor. I put the unit that I want to get on top, and I put the unit I want to get rid of on the bottom. These units cancel. I'm left with my moles, and I keep going. I'm continuing on. Okay? Okay, what about moles to grams? I just do it in the exact opposite way. So if I have 4.43 moles of potassium, that is not the right answer. Somebody do that calculation for me. What is it? Okay. If I have 4.43 moles of potassium, and I want to convert that to the number of grams of potassium that I have, okay, then what's it going to be?
173.213.
Okay. So 173.213. Okay, grams of potassium. That's how many grams of potassium it is. Just okay. Okay, now, what if I want to convert from atoms to grams or grams to atoms? So, you could do it in a two-step process, but you don't need to because intuitively you can consider that these are the grams. These masses right here are grams per mole, right? 69.72 grams for every 1 mole. Or you can think of them as 6.972 grams for every 6.022 times 10 to the 23rd atoms. Okay? And that way you kind of skip a step. You don't have to do a two-step process. So here, if I'm going from atoms to grams, I could go atoms to the moles to the grams. But I don't need to, because I can go straight from the atoms to the grams if I know what this atoms number represents. It represents 6.022 times 10 to the 23rd atoms of potassium. Okay? Okay, you can see how that would just, here the moles would be 1 anyways, and the atoms would be 6.022 times 10 to the 23rd. And you would have your grams divided by your atoms in any case, okay? Because the ones right here, the mole is 1 mole, they just cancel anyways. So it's kind of an extra step that you don't need to do. If you understand it that way, then do it, but you don't need to do it that way, okay? It's not necessary, okay? So I can set it up atoms to grams, my conversion here, and simply do the number of atoms times the molecular mass divided by the atoms in a mole, which is 6.022 times 10 to the 23rd. Okay, And then I'll find my answer. That's how many grams are in 5.43 times 10 to the 15th atoms of potassium. It's a very small number. That's because that's not a very... I would need 6.022 times 10 to the 23rd atoms of potassium to have 39.01 grams of it. I don't even have close to that number of atoms. So yes, it's a lot less than 39.01 grams. And if you're going the other way, if I want to figure out the number of atoms in a specific amount of grams, this would be kind of a more practical one. So I have 125.6 grams of potassium. How many atoms? This one is not, sorry. This one did not get set up. Okay, so if I have 125.6 grams of potassium, and I want to figure out the number of atoms that I have, okay, then I set it up. Atoms are on top, grams are on the bottom. Atoms, the number that goes with atoms is always 6.022 times 10 to the 23rd. So wherever I see atoms in my conversion factors, I'm always using that number, 6.022 times 10 to the 23rd. Wherever I see grams, I'm always using these numbers. So for potassium, it's 39.10 grams. So how many atoms then are in 125.6? It should be more than this, right? Because 39.10 grams would be one of these. So how many are there of those in 125.6 grams of it? Okay, yeah. I was going to say, there's something missing there. Times 10 to the 24th. Okay? Which is more than 6.022 times 10 to the 23rd, right? So that's how many atoms we would have. Okay? We'll stop there. We'll see you guys Monday. Make sure you're getting your Chapter 2 homework done. And if you weren't here for roll call, please come see me.